Below are several implicit equations which haven't been solved for any particular variable. The variables involved are x, y, and z. So if any of these are functions, they would be multivariable functions. Typically what we'll do here is we'll solve for z. And we can plot it using an online multivariable equation plotter. Now we want to think about the same rules that apply to one variable functions and now extend them to two variable functions. So you may recall when it comes to a one variable function, let's take the example of y equals x. To qualify as a function, a curve has to pass the vertical line test, which means that when you draw any vertical line anywhere on the x-axis, it should only intersect your function once. If it intersects more than once, then what you have is not really a function. So whereas y equals x satisfies that, a circle would not. Let's take a look at a circle equation now. Yeah, so a circle would actually fail the vertical line test because a vertical line can intersect the circle twice. Now let's attempt to draw some multivariable functions. But whereas single variable functions are lines and curves, multivariable functions are going to be shown as surfaces. So when we have a single variable function, it's plotted on a two-dimensional axis as a line or a curve. But what we're going to do now is we're going to plot multivariable functions on a three-dimensional axis, and they will be drawn as surfaces. There's many online web applications you can use to plot these surfaces. I'm going to start off with this one here, GeoGebra. All right, let's try the 3D calculator. All right, we'll be able to type any equation here on the left. And let's just start with an easy one. Okay, now the first thing is let's look at these axes here and see how they're defined. The red is actually our positive x-axis. The green is our positive y-axis. And the blue is actually positive z. So you can imagine this as if somebody took a piece of paper and had laid it down on a table, right? And then here is how we normally look at the x and y axis. Now you can tell that it's positive x because there's a arrow over on this side and not on that side. That's a convention that's often used in math to help people understand which direction is the positive x. This is the positive y-axis, of course, and the z comes out of the page. But when we rotate things three-dimensionally, we'll often look at it in this sort of orientation, where the z is up and the plane is sort of laying down. All right, now what I want to do is I want to plot my first 3D function here. Let's try to make just a simple horizontal plane. Well, all that requires is z equaling a constant. You can start off with a constant of perhaps 0, which is the xy plane itself. We can move it up, and then move it up some more, and move it up even more until we can see that, yeah, okay, we're at a z of 3 up here, and that's where the plane intersects our z-axis. We could go back down to 2, back down to 1, or even up to 4. We can go in the negative direction. And these are some of the most basic three-dimensional functions that we can draw. Let's try some other types of planes, perhaps a slanted plane. We could do z equals x. Okay. Or perhaps z equals x plus y. We can change the orientation of the plane. Okay. And what if we were to eliminate the z altogether and get perhaps x equals 0? Okay, now we have a vertical plane. This is a vertical plane that is drawn along the y-axis. Just like x equals 0 would be a vertical line in the two-dimensional sense. Okay, when we extend this to 3 dimensions, plot in 3 dimensions, becomes a plane. Let's try the familiar y equals 0 and see what that's like. Okay, now we have what in 2 dimensions would be a horizontal line, but in 3 dimensions, it's a plane that intersects the z-axis, and it also intersects the x-axis. But the y is fixed, so it can't, so none of the points can have any variation in the y direction. All right, so that's just a little introduction to this. You can play around with it yourself and get the hang of it. What I'm going to try next is, let's decide what is a function. Is z equals 3 a function or no? Well, it turns out it is a function. The reason why is we never get more than one z value for every x and y input. So how do we find the different x and y inputs? Well, take the point 0, 0. That's located at the origin. You want to trace it up and see how many times you intersect with the surface. And it's only once, right? Now what if we move that point around to 0, 1 now and trace it up, and it only intersects once? And what if we do 1, 0? Trace that up, and it will only intersect the plane once. So it's still a vertical line type of test that we're doing. And as long as we only intersect once for every combination of x and y, then it's a function. So z equals 3 is a function. Now let's try a little bit tougher one though. Let's try this. Let's try a sphere. Z squared plus x squared plus y squared equals 1. Okay. And maybe let's make our radius just a little bit bigger. Okay. Now, take any given point on the coordinate plane of x, y. Take the origin, for example, 0, 0. Now, if you were to draw a vertical line along the z-axis here, how many times would you intersect the surface, right? Well, you'd intersect up here at the point 0, 0, 2. That's one intersection right there. And you would also intersect at 0, 0, -2. And that's a problem because there are two outputs for the input of 0, 0. That makes a sphere not a function. Okay. Now, if it had been just a half sphere, then that would have been okay. It would have been a function. How do we write a half sphere? Well, we have to take the equation and rearrange it, making 4 minus x squared minus y squared, moving the terms away from the z. Okay, it's still a sphere. But now what we want to do is we want to take the square root to get z alone. Take the square root, though. Let's see what that makes. Okay, that makes a hemisphere. And the reason why is I didn't put the plus or minus here, but I should have. Whenever I solve z squared, an equation involving z squared equals, I have to take the square root of both sides. But we have to put plus or minus in front of the square root when we do that. So that means if I want to truly graph this correctly, I'm going to need two parts to it, a positive and a negative. And this is the true solution to that original equation. But this shows how it's not a function because the surfaces overlap, where if you did a vertical line test, you would touch twice. Okay. All right, so that's going to be how we'll tell if a surface is a function or not, is we can look at it visually here, and we can also use a little algebra to decide whether it looks like z could be more than one output for a particular x and y input. All right, so let's take this xz squared plus 2xy minus y squared equals 4. Okay, that's a long one. It's a pretty complicated expression, so let's just solve it a little bit. I'm going to move these terms to the other side. Okay, then let's divide by x. So I'm going to solve by square rooting it myself. And I can't guarantee that the program will always be able to recognize every implicit equation. We may have to solve ourselves a little bit here. Okay, so here's 1/2 of it. And we can zoom out. Does it look like a function so far? I think so far, yes. It looks like it would pass the vertical line test. But I didn't put in the plus or minus. That's the problem. So I need to get one more of these. And now we can see the surface would fail the vertical line test now because it has a mirror image in the negative z direction. All right, so just so that we can see that it would fail the test, we could create a vertical plane. We could type in y equals -5. Get a vertical plane here. Then we could intersect that with another vertical plane, x equals -5. And all we're looking for here is 2 points where it touches the curve. And we can see right about there, this vertical line will touch our curve at a positive z. And then also it touches again at a negative z. So there's no question, this is actually not a function. Okay, now let's try some of the others here. Alright, yeah, and once again, it's having a little trouble recognizing how to draw the surface, so I'll just rearrange the equation a little. Alright, now that I moved the terms over myself, we can look at the surface. And here, even though the surface seems to go kind of vertical, it's not perfectly vertical. It's still sloped just slightly, just like the ln x function is sloped. And ln x, of course, is a function. And so this is a function as well. Okay, now in this third one, that's going to be a little bit of a challenge because it's got a z to the third power. I'm going to move the terms over, and then I'll be taking the cubed root. Alright, so what I typed in was z equals 6 minus 2xy plus x squared minus y, and then I took the cube root of that. The cube root does not give us two answers for every input, and in fact, y equals cube root of x is a function. And if we check out our surface, we can see that this is a function too. It passes the vertical line test. So I'll write yes for that one. The next one's going to be a little tricky because we're going to need to factor the z out. All right, so let me do that. Pull a z out front, leave behind x cubed plus 2xy, and then we'll add the 4xy term to the other side. Now we can divide. And we're going to have z equals 1 plus 4xy over x to the third plus 2xy. Let's see what it makes. Oh, wow. Okay, and all we're looking for is evidence of, are there any overlapping surfaces in a vertical sense? I don't really see any overlapping problems. We have some places where the function heads toward infinity, an asymptote in the three-dimensional sense, but we don't have any problems like a sphere would. So yeah, I'm going to put yes, this is a function.